Hi, this is the first video in a series of videos on LCD displays, and more specifically, how you can go about getting, or what steps are involved in, designing and manufacturing your own custom LCD display. Hope you enjoy it. Let's take a look at it. Now, LCDs come in all shapes and sizes. As you can see here, this is just some of them. You got your traditional low-cost reflective static LCD display, which we'll have a play around with in a minute, so stick around. And you've got your traditional 2 line by 16 character LCD display module, and you've got character-based ones and graphical-based ones, and you've got ones that are on mounted on PCBs as part of modules. You've got ones that are just have a flat flex coming out of them. You've got ones that have got drivers on them. You've got ones that are low pin count serial interface ones. You've got 7-segment, 14-segment displays like this one we'll have a look at. You've got graphical display ones and all sorts of things. Let's take a closer look. Now, of course, you can buy fully custom modules like these, which have all the driving circuitry and everything else on, and you just talk through a pin-based interface, be it a flat flex like this, or just your regular through-hole type stuff. And these are fairly inexpensive these days, but hey, you can actually do better costs than these, which is what this video series is ultimately about, is designing and manufacturing your own low-cost custom LCD display. First of all, we'll briefly cover how an LCD works, and these images, most of the images I'm going to show you in here are taken from the very excellent microchip application note AN658. So I'll link that in down below to check it out to get a bit more detail, and you can actually deep dive down the rabbit hole on how LCDs actually work at the chemistry and physical level, but we'll just keep it very simple here. Now, let's take a look at the basic LCD components. There's a front polarizer on top, then there's the backplane electrode, which is basically for all intents and purposes, like the negative common type terminal. And then you've got the LCD fluid itself. It's actually just like a pocket of liquid crystals, and we'll take a look at an electron microscope photo of that in a second. And then you've got the actual segments etched onto a glass layer, and they go off via little conductive paths to the actual pins, and the shape of those, how you design those, determines what shape segments you get on your LCD. And then you've got a rear polarizer at the back. Now, these polarizers can be combined in various ways to get you a positive LCD, which is what we're going to look at now, or a negative one, which is basically white segments with a background, or positive will be black segments that you're more familiar with on the white background. Now, light polarization is key to how LCDs work, and I'll give you a crude demonstration with my watch and my polarized sunglasses here. If I put my sunglasses like that, you can see the LCD no problems at all, but if I twist it like that, you'll see it eventually vanish. There you go. And that's basically how the key concept behind how LCDs work. Now, the LCD we're going to talk about here is what's called a twisted pneumatic, or TN type display. There are different technologies of how the actual liquid crystals themselves work. You don't have to concern yourself too much, but suffice to say that there are different states of these liquid crystals. So most LCDs you're probably going to come across are of the twisted pneumatic type these days. And here's a really cool electron microscope photo of the liquid crystals and how they can line up under an electric field. And this is the key to how LCDs work. You've got the top and bottom electrodes there with the liquid crystal fluid in there, which is affected by an electric field. Essentially not a current, it's just an electric field between the positive and negative plates. And that can change the orientation of the liquid crystals themselves. And let's have a look here. The LCD on the left there, the LCD orientation with no electric field, and you've got the twisted pneumatic liquid crystals in there. In this particular case, when there's no electric field applied, the light will pass through, reflect off the reflector at the bottom, and come straight back out. So you effectively, the light is not blocked at all. So you essentially see that white or silver type background, segments not on. But on the right hand side here, when you've applied an electric field, all of the liquid crystals line up like this, it's a bit counterintuitive. They line up, so you would think that the light would pass back through, but it's actually the opposite case because of the polarizers in this particular case. When they all line up like that, the twisted pneumatic crystals in there will not reorient the light, so the light is actually passes straight through and then is blocked by the polarizers, and the segment appears to be on or black. And of course you can, as I said, you can change the polarizers around the configuration to get either white characters on a black background or black segments on a white background. And also, temperature can play a role in the LCDs as well. The poor little liquid crystals actually get pretty lethargic if you drop them, if you drop the temperature. And you can see this one here I've actually had in the freezer for a little bit, and you can see it a little bit lethargic compared to the other one. It just takes a little bit of time for those segments to decay, and that can take, like, hundreds of milliseconds if it gets cold enough. Once it gets towards 0 degrees or below, it can be very significantly affected. So LCDs are not current driven, they're actually electric field driven, which essentially makes them zero power, apart from the capacitive nature of them, and you have to switch at a certain frequency to make it visible, and then you have to switch that capacitance. So you do get some current through that capacitance, your basic capacitive reactance formula there. But I can actually demonstrate this by not actually having any power at all. I can actually turn on these segments. It's a bit higgledy-piggledy, but you can see that I'm just the electric field picked up by my body and then superimposed across. In this case, I've got a ground hooked up to the common pin. It's going back to mains earth, and you'll see that we're able to get the segments to come on and stay on, and you can see that they do actually decay away like that. So there can be a bit of charge build up in there on the actual display, and then it can take time for them to fade out like that. Cool, huh? Now you can actually drive LCDs with a DC voltage, but don't, because that is the incorrect way to do it. You'll ruin your LCD. It will destroy the liquid crystals in there, and magic smoke will escape and it won't work anymore. The only correct way to drive LCDs is with an AC voltage, and I'm actually driving it at the moment, as you can see, with a basically a DC voltage, 6 volts peak to peak with a 3 volt offset. So that's basically a 6 volt TTL type, digital signal at 0.1 hertz. So it actually flashes off and on. So you can technically do that, but don't. What you actually want to do is have a proper AC signal like that, so there's no offset. So I've just got a 6 volt peak-to-peak AC signal. So you can see in the middle there, it's going positive, negative, positive, negative. So the average DC value is 0, and that's what you want when you drive in an LCD. You want an average DC value of 0. Otherwise, you'll eventually kill it. Now, I'm actually driving this segment at 6 volts peak to peak AC with 100 hertz. This data sheet actually says to do 5 volts, but it doesn't specify RMS or peak to peak. Now, we can actually adjust the amplitude here. I'm going down. If I do it at 5 volts, you can see that it starts to affect the contrast, and that's 4.5. It's basically almost vanished, and at 4 volts, it's gonski. 4 volts peak to peak for this particular one is not enough. A common drive voltage might be, at least 3 volts or something like this. This one needs at least 6 volts peak to peak to be dark. And of course you can go up, and that might increase the contrast, but don't go too high, otherwise you can get ghost in between segments. Now, I'm actually driving this at 100 hertz at the moment, but you can't just say switch down to 1 hertz, because if I do that, you'll see it's still basically on. Trust me, I've got that at 1 hertz. Now, if I drive this at 0.1 hertz, you can see it's sort of fading out like that. That's not the correct way to do it. The proper way to actually drive it is to apply your frequency or not. So that's 100 hertz, and you can drive it, you don't have to drive it any lower than that. That's just, so it doesn't flicker or anything like that. So we're driving that at 100 hertz and on, off, on, off, on, off. That's it. But you definitely don't want any DC bias. If you want to go off, you actually just tri-state your pin, your driver pin like that. Now this is your most basic type of LCD. You've basically just got your raw LCD glass and the pins like that. There's no additional circuitry. Now these actually come in two types. One is with the through-hole pins like that, which just clamp top and bottom basically like that, or you can just specify the exact same LCD but without the pins. It's exactly the same glass, but if you order them without the pins, then you need to use them with what's called an elastomeric connector, otherwise known as a zebra strip, which is basically, if we can get that off there, it's a conductive rubber strip like that, which just connects through to the glass. You might be able to see the actual contacts on the bottom of the glass down there. So you can either tell the manufacturer to just give you the raw glass like that, and no worries, I'll use an elastomeric or zebra strip, or you can ask them to provide a strip to your specification, or you can just order it with the through-hole pins attached. Now the next step up from just your basic glass, either pin or elastomeric connector, zebra strip connector, is a flat flex connector. Once again, it's exactly the same glass, but you can get them to use a conductive glue that basically sticks the flat flex cable onto there, and it goes straight out to pins like this. You're not actually reducing the number of pins in any way. You're just merely, they're just three different types of interfaces that you can get to a regular LCD glass like that. And the thing with any of those three interconnect solutions, you've basically just got your LCD glass, and you need a separate driver. So you need all the driver circuitry on the bottom there, either a microcontroller, which has the built-in LCD controller, which we'll go into in a future video, or whether or not you use a dedicated LCD driver chip, or you can bodge your own driver circuitry. We might go into that, but you need some sort of AC drive circuitry for the display, because these things don't drive themselves. You can't just hook these up to a microcontroller and expect them to work. They're just a raw glass. They need that AC signal, and they're going to be often multiplexed displays. So very complicated to actually drive these things. So you need a dedicated driver chip, basically. So basically, the next step up from your raw glass is, of course, these dedicated modules, which have all the driver circuitry and everything built in. But that's quite expensive. You've got a PCB, you've got, components and all sorts of stuff on there. Like, you can get these reasonably cheap, but if you're talking really high volume, it's not that terrific, and the height, form factor with the PCB and everything else can impact your design. You can't do like really ultra tiny designs and things like that. So your next step up from that is to get your driver chip built onto here. Can you see it? Can you see it? That's it down in there. Now this is actually called a chip on glass, or COG solution, and that's actually the driver chip built into there. So you can see this actually hasn't got many pins at all. This is actually 132 by 32 dot matrix graphic LCD display. So the LCD display is all multiplex and everything. It's got a lot of lines on there, a lot of contacts, and they go into the embedded chip, which they mount on the glass on there, hence why it's called chip on glass, because the glass actually extends right out to the edge here, and then they've only got like a simple serial interface. So it takes all the headache out of driving this LCD. This one's, nice and thick because it has like a huge backlight and things in there, but if you actually take that module out without the backlight, it's pretty thin. The chip is just on the glass. And another variation of that one, here we go. This one's also got a backlight, but the backlight just pops off like that. There you go. And that is like just the same, really, as our glass that we had before, but it's got the driver chip built onto it, the chip on glass. This one's not a serial interface. This is like a parallel interface one, just like it actually might simulate the interface on your standard 16 by 2 LCD. I think this one is a 16 by 2 LCD dot matrix actually, and it's got your standard interface, but all the driver circuitry is built on there. Look how thin that is. Awesome. Or if you're not a fan of chip on glass, COG, you can actually, this one before I lied, this wasn't just the flat flex coming out. If you look at there's a little bulge in there. That's actually what's called chip on flex. So this one actually has the driver chip. Once again, a standard, Hitachi LCD driver interface, but the driver chip is built onto the flat flex like that. And that you may prefer that for some system interconnect reason or something like that, rather than a pin-based one like this. But just be aware, the result is exactly the same whether or not the driver chip is mounted on a flex like this or is mounted directly on the glass. When you're getting a custom LCD made like this, you can just specify, I want COG please, I want chip on glass, and they will just extend the glass out for you. They'll put the chip on there like a standard Hitachi chipset or whatever it is, whichever type of interface you specify, and they will give you that for like, I don't know, like 50 cents extra, $1 extra per display or something like that in, reasonable like 1,000 odd volume or something like that. So it's not necessarily a hugely expensive solution, but it can actually be ultimately cheaper, as we'll go into a future video, to just get the raw glass and use an external driver chip that way. And so these aren't too expensive, but if, you're counting every single cent, then this may be more solution than this plus a driver chip. Now, to confuse the issue even more, LCDs, all different types, come in 3 different varieties. In addition to those 3 different solutions we saw for the interconnect, this one has to do with the optical properties of the LCD glass and the module itself. The first one is reflective, the next one is transflective, and the third one is transmissive. Oh, goodness. Now this particular one here, for those playing along at home, there's the DigiKey part number. This is a reflective LCD display, and what that means is that it is not compatible with a backlight. You might be able to edge light the thing or something, but it's basically not compatible with a backlight. It's got a mirror reflector embedded on the back in there, and you basically have to shine the light from externally through the glass, and then it reflects back out. Now these reflective types, in my opinion, have by far the best contrast and view angle and stuff like that, although that varies with process technology and other things. So, but basically, if you want the ultimate contrast in an LCD, you want a reflective type. But the disadvantage is they're no good in low light because you've got no backlight. Once you're, in like dark conditions, you're screwed. But the reflective type, basically, once you've got good external light, it's the holy grail of display quality. So your next type is what's called transflective, and that's what this one here is. And it's hard to sort of, tell the difference. One has like a white background and one has this kind of, a silvery type, or it could be, some other type of backing on it. And transflective tries to get the best of both worlds, tries to get the optical properties of the reflective one while still allowing light to shine through from the back here and actually give you low lighting conditions. And you can see this one has the backlight. You can see the 2 PCB mount pins here. This is just the LED on here that allows you to have your backlight like that, and it shines through. So you can use it with or without the backlight. But the disadvantage is transflective isn't quite as good a optical contrast quality as you'll get on a pure reflective like this. But it's probably the best overall solution if you want to use your display in all sorts of lighting conditions. You simply choose to turn the backlight off or on. Just like, you're used to your multimeter. Most good multimeters will have a backlight on it. They're using transflective displays. And the third type is what's called transmissive. And I didn't actually have an example here in the lab of that, but it basically, here's a graphic about it. You basically must have the backlight on it to make it work at all. There is no reflective or semi-reflective backing on it. It's purely relying on the light source coming from the back instead of coming from the front. And that's great if you're always want a backlight and you want it to work in all conditions. It can, but then the backlight is always drawing power. You don't have the option to turn that backlight off. It'll basically become unreadable if you remove that light source from the rear. Now, transmissive displays are very common, like your TV, for example, will use a transmissive display. It's always on. It requires that backlight. But if you want to use them outside, then you've got to have a really bright backlight on it continuously to overcome the external ambient sunlight. And that can be really difficult for outdoor type displays, or more to the point, very power hungry. But in small displays like this, you won't often find like a small, that you'd use in a product like this. Transmissive isn't all that common. You usually get the transflective type or the fully reflective type. So your standard reflective display like this one is your cheapest and your simplest because it doesn't need a backlight. It's going to be the thinnest, whereas your transmissive one, actually, you're going to have to need the backlight on the back of it, because you wouldn't want to use a transmissive one without the backlight. If you know you're not going to use the backlight and you're not even going to integrate it into your product, it'll still work, but not as good as a reflective one. So you've got to decide up front whether your product is going to have backlight in or not. But there we go. I can generate numbers. Beautiful. Anyway, we'll go into driving them in a future episode, but there are basically two different types of LCD. This one that we've got here is a static type. If you take a look at the data sheet, it's what's called a static or a non-multiplexed LCD display. So what that means is that it's got one common pin down here and then a pin for each particular segment on the display here, and basically there's no need to multiplex anything. You still AC drive in the pin, but you don't actually need to multiplex different segments. And this is common for like a display like this, which doesn't have many segments on it. In this case, it's just a 7-segment display like that. And, we have X number of pins. This one actually has 2 pins per segment, so you don't need that many pins. And, maybe like a 3.5-digit multimeter, one of those real cheapo ones. They might be static as well, because you can get away with like 40 pins or whatever. And you can drive those statically. There's no need to multiplex. But once you get into a more complex LCD, which is what we're going to actually design in this series of videos and actually get manufactured, you'll see that in the next video, is that you need to multiplex the pins. You need to have more than one common pin on here, and then you need to multiplex the segments. Otherwise, you'd end up with hundreds and hundreds of pins, and you obviously don't want that because it's logistically very difficult to drive. You need a multi-100 pin LCD driver chip and everything like that. And of course, it goes without saying that your graphical ones like these, or your, even your text-based graphical dot matrix ones, this is an 8-character by 2-line, and this one here is a 16-character by 2-line LCD that you're familiar with. They're actually dot matrix, and because there's just so many dots on there, these ones are, by default, they have to be multiplex. There's just no other way to do that with the sheer number of dots. But if you've got one like this one, which is an 8-digit 14-segment, look at this puppy. It's one of these starburst displays. I love these classic old school starburst, right? This has, if you count up the number of segments on there, it's 8 by 14 segments. Clearly, we don't have that number of pins. So what this one is it's actually got 4 commons, what's called 4 common pins, instead of this one here, which just had the 1 common pin, and then you have to actually multiplex. If you want to turn, like in theory, your product could turn all these segments on at once. And if you want to do that, of course, then you have no choice but to multiplex the display using those 4 different commons, just to reduce the number of driver pins that you got on there. Oh, sorry, I love these. I just love them. Starburst. Oh, brilliant old school stuff. If you don't know about the Starburst, it's just a way to allow you to display alphanumerical characters in a standard 7-segment type format. But it uses 14, and you can also get 16 segment ones as well. But they're very cool. And you'll find that most LCD driver chips built into microcontrollers will typically have a maximum of 4 commons, but we'll go into this in the design video in the next one. So there you go, that's just an example of a multi-common multiplex display. But the problem with your multiple common displays like this is that they require, the more commons you have, the more bias voltages that you actually require to bias the various commons, and that's probably a video in its own right. But suffice it to say, they're a bit more complicated to drive than your general static display or non-multiplexed display like this one, which has basically 1 common. So you really do need a dedicated driver chip that handles the multiple bias voltage levels for these multi-common displays. So there you go, that's a look at basically the 3 different interconnect type solutions for custom LCDs, and also the 3 different optical properties of LCDs like this, and you can get them all in any weird and wonderful combination that you like. So in the next video, we're actually going to look at actually designing your own custom LCD display, and ultimately in future videos actually getting that manufactured and then driving that for our custom product. So stay tuned for that one. So I hope you enjoyed that, and if you did, please give it a big thumbs up, because that always helps a lot. And as always, discuss down below in the comments or on the EEVblog forum. And don't forget to subscribe and, you know, do that bell icon so you get email notified and all that stuff YouTube has to, you know, YouTubers say. Oh, and yes, thank you to my patrons over on patreon.com. I've had a Patreon page for ages where people support me directly because of the adpocalypse these days. I'm not losing a huge amount of money on videos, but I'm getting more and more videos demonetized. So a lot of YouTubers like myself are moving over to direct sponsorship from the viewers on places like Patreon. Really appreciate it. Catch you next time.